The second most important element of CNNs is the pooling layer. Contrary to the convolutional layer, the pooling layer operates independently on every channel, depth slice, of the input volume. This is a major difference with the convolutional layer, for which each kernel operates on the whole depth of the input volume. The pooling layer applies a given operation on different areas of the image, and a spatially reduced image is obtained. Let us look at a simple example. On the left, you have an image. Let us fix the spatial extent of the pooling to 2 and its stride to 2. Then we consider the first area in blue of size 2 by 2, the size of the spatial extent. We apply a function to all these elements, here the maximum, and obtain one value that we put inside the corresponding output. We slide the window by 2, since the stride is 2, and repeat this procedure. The two most important types of pooling are max pooling, in which the function maximum is used, as we have just seen, and average pooling, in which the average is computed instead of the maximum. Contrary to convolutional layers, pooling layers do not have any trainable parameters. Indeed, once the spatial extent and the stride have been fixed, and once the function to be applied has been chosen, there is nothing left to tune. Usually, these hyperparameters are specified before the training. As I mentioned, pooling layers operate on each channel separately. It means that the depth of the output volume of a pooling layer is always equal to the depth of the input volume of a pooling layer. Pooling creates summary statistic, here the maximum, of neighboring pixels. Pooling helps the representation to become approximately invariant to small translations of the input, because only the value of a maximum is stored and not the exact location. In our previous example, we know that the maximum is to be found in an area of 2 by 2 pixels, but we do not know exactly at which pixel. Thus, if a small translation is applied to the input, the output of the pooling layer is almost unchanged. It is useful if we care more about the presence of a feature than its position in the image. Pooling also allows us to handle inputs of different sizes. We will detail that at the end of the session. We are now going to see a simple example of a CNN to see how you can organize the different layers together. This is a simple and specific example of CNN, and we will see more complicated architecture afterwards. For this example, we consider only grayscale images. First, we can apply a convolutional layer. As we've seen, one kernel produces one feature map. We may want to produce more than one feature maps. For example, 2, as depicted here, or 3, 4, 5, or even 6. Let us stick to 6 feature maps. After the convolutional layer, you may apply an activation function to each entry of the volume. For example, a ReLU function can be applied to each value of the output volume. Then we can apply a pooling layer. Remember that a pooling layer has no trainable parameters, displayed in orange. A first feature map is created based on the first input feature map by applying pooling to different locations of the feature map as seen before. The process is repeated for the second input feature map, which creates an output feature map, and again, and again, and again, until the operation has been applied to all input feature maps separately. The two consecutive layers, convolutional and pooling, can be summarized with this scheme. We can pursue by applying another convolutional layer. The only difference with the first convolutional layer is that this one operates on an input volume of depth 6. Therefore, the depth of the kernel is also equal to 6, which means that the kernel can no longer be represented as an image in orange. Instead, it is depicted using a volume. This volume corresponds to one kernel, which creates one feature map. As before, you may want to create more than one feature map. To do so, you need to consider more than one kernel, say 6, for example. As you notice, there are numerous parameters that will need to be trained. The whole architecture so far can be summarized with this scheme. Following the convolutional layer, you can apply an activation function, which is not represented here, and another pooling layer. Let us now look at what happens after this layer at the end of the network. Let us take a step aside and consider this simple example, a 3x3 image. To go from an image to a classic neural network that may be used at the end of the network, we need to flatten this image. Flattening an image means forgetting about its spatial organization and considering instead the set of pixel values it contains as displayed here. This operation is done for all feature maps of the previous layer, which gives a large number of neurons. Note that this operation takes a volume of feature maps and outputs a set of neurons. We can now summarize the architecture we have described. After the flattening layer, one can choose to add dense layers, also called fully connected layers, before the output layer. Note that here, the dense layers contain trainable parameters which are not represented in orange, but that will be optimized during the training phase. So here is a possible network architecture which allows you to see how the different types of layers can be organized in a CNN.